Okay, so let's look at equations of motion for mechanics. Before now, we know how to describe the motion of an object using a graph, but sometimes that can be a little clumsy and it just can get a little more difficult to explain exactly what's going on, and then we can't get instantaneous and it just gets clumsy. So that brings us to equations of motion, and there's a couple of things we need to keep in the back of our minds right off the bat. First of all, when are we allowed to use these equations of motion? So the first thing is that it must be linear motion. So it's straight line motion, and linear means that the acceleration remains constant. So we're not going to change the acceleration. It can't be changing acceleration. And if the acceleration changes, so it goes from, for 1 second, it's 2 meters per second squared, and then there's another set of motion where, say, it's 3 meters per second squared, we have to do another set of equations. And secondly, well, that's what I said, constant acceleration. That includes no acceleration. In other words, that includes when acceleration equals 0. All right? So here are our 5 equations, and they are given on the information sheet. So it's not like you have to learn them, but knowing them is not a bad idea, because then it helps you. It's going to be less complicated for you. VF means final velocity, V for velocity, F for final. VI, initial velocity, so final is at the end, initial is at the beginning. All right, fairly straightforward. A is acceleration in meters per second squared. Delta T is time in seconds, and then delta X is the displacement in meters. You'll find for most of the equations at this stage, you'll probably use the first 3 equations the most. We don't use the last one as often as we think we will because of needing to know that acceleration remains constant. So you need to be careful when you use the last equation, because that really does need to make sure the acceleration didn't change anywhere during the motion. What do you need to do to solve problems? Well, first of all, always write down what you're given with the correct SI unit. This is especially important for velocity. And remember that to go from kilometers per hour to meters per second, you divide by 3.6 to get it into meters per second, okay? Then write down what you have to calculate. You'll see when I do these, I have a specific order that I do it in, and it makes it easier to decide on the equation. Choose a direction as positive and stick to it. Usually I choose original direction. Original direction. So whatever direction the object was going in first. Then choose your most suitable equation. Substitute in the values. No, don't use the units. Do the calculation. If you've got a vector, so this is pretty much everything except time. Remember, you must give me a direction at the end. If they ask for a magnitude only, then magnitude means that positive answer, okay, at the end, but I don't need a direction. Which is what I just wrote in the next one. There we go. So, remember, if an object starts from rest, initial velocity is 0. This is an implied piece of information. If an object comes to rest or comes to a stop, final velocity is 0. They're not going to tell you that. It's implied. A is positive if it moves faster. Okay, the acceleration is the same direction of the motion. A is negative if it becomes slower. So the acceleration is in the opposite direction to the motion. We've now laid the foundation. Best way to learn how to do this is to do examples. And of course this. Constant and uniform, same thing. Okay, means exactly the same thing. So, I've underlined and put into color the important words. You really need to be able to work these out from the question. So, a car starts from rest, accelerates in a southerly direction at 3 meters per second squared. I'm taking southerly as my positive direction because it's what's given to me. From rest means initial velocity is 0. It accelerates, so I have an acceleration. And what they tell me is that acceleration is 3 meters per second squared. Then they want us to calculate the velocity. So this is a final velocity after 10 seconds. That's delta t. So south is positive. Now, I always write my information in the following format, and I'll show you. So my final velocity is what I'm looking for. Initial velocity was 0. Acceleration was 3. Time is 10. Now, if you look carefully at this, you'll see that it's just going down, is the first equation that I gave you. Vf equals Vi plus A delta t. Vf equals Vi plus A delta t. That's where I get that format from. Doesn't matter which order you put these in. I don't know delta x. I may or may not need it. But from looking at the order I've got that in, and then I go to my equations, I go, well, actually, this is the most logical equation to use. I don't know delta x, so I can't use any of the other equations. So Vf equals Vi plus A delta t. Straightforward substitution. 0 is 0. 3 times 10 is 30. Use your calculator if necessary. And I get a positive answer, which means my answer is 30 meters per second south. Nice and straightforward. Now they say, same question. Calculate the distance, delta x, in 10 seconds. So now I look at the information. So if I go back to the information I've got here, I need delta x. Okay, that's what we're looking for. We have an equation that says Vf squared equals Vi squared plus 2A delta x. And I've got one that says delta x equals Vi delta t plus a half A delta t squared. I can use either of these equations. Choose the one that's easiest to work with, and that's one where you don't have to change the subject. And also try and choose one where you haven't had to work something out to use that equation in the first place. So I won't use that equation, the first one, simply because if I've got the wrong final velocity, I'm going to carry it down into this equation. That's the first reason. Second one is I'm going to have to solve for delta x. It's a long way around. Do the easy one. That equation, delta x is already the subject. So delta x equals Vi delta t plus a half A delta t squared. Substituting everything we know, and 0 times 10 is 0. Then we've got a half times 3 times 10 squared. You put that into your calculator, and we get 150 meters south. Okay, straightforward. The last question now goes back to what we learned at the beginning of this section. Calculate average velocity. Average, remember, is total distance divided by total time. My object was accelerating, so the velocity changed. Oops, and I went and wrote, wrong one too. Let's take that up. There we go. Okay. 150 divided by 10, so it's 15 meters per second south. My final velocity was 30. My initial velocity was 0. My average is going to be somewhere in the middle. This one happens to be 15. It doesn't always work like that, okay? But that's my average. Total displacement over total time, okay? Let's do another one. A motorbike rider is riding. Let's change the pen color just because we can. Let's make it blue. Is riding at 40. Initial velocity. When he needs to brake for a red traffic light, he needs to stop, Vf, within 200 meters, delta x. First thing, what is his acceleration? Well, this is a diagram of the situation, okay? His initial velocity is 40, his final velocity is 0, and he's going to go 200 meters. Drawing a diagram is always useful. It helps us decide what's going on. So, because he's coming to a stop, I know that the acceleration I calculate must end up being a negative value. All right? Because he's slowing down. Now, I know his final velocity is 0. And we really should have put meters per second there. His initial velocity is 40. His acceleration we don't know. Time we don't know. And delta x is 200. So now we need to make a decision. I'm not going to use an equation that has time in it because I don't know time. Yes, I could work it out first and then calculate the acceleration, but that just doesn't make any sense. We do have an equation that doesn't have time in it, and it's this one. Vf squared equals vi squared plus 2a delta x. If we substitute in what we know, so 0 squared equals 40 squared plus 2a times 200. I did all the maths here, so 0 equals 1600 plus 400. We're going to take the 1600 over, then divide by 400, and we get minus 4. But remember, we can't leave the answer as negative. It's got to become a positive answer with the direction inwards. Now, how did I know west was negative? Because by default, it was originally going east. I have made east my positive direction. Then the second question was, how long does it take to stop? Well, I know acceleration. We've already worked it out. And it's minus 4. So when I substitute it in, it's minus 4. So I get 10 seconds. What I need you to recognize at this point is I could have as well, if I had wanted to, use the equation delta x equals vi delta t plus a half a delta t squared. Because watch, this is 200. My initial was 40, and we want delta t plus a half minus 4 delta t squared. Now, if you look at this, you can see that perhaps this is going to become a little more difficult from a maths point of view. All right, because we're going to have 240 delta t minus 2 delta t squared. You've got a quadratic equation. We have 2 delta t squared minus 40 delta t plus 200 equals 0. Take out the 2. Oh boy. And now we look at this and we go, oh my word. Now we have to use quadratic functions, and we have to, now you'll end up doing it as a quadratic, and that's a minus at the end, that's a plus. Oh, life gets interesting. So you know what? We avoid using that one if we can, okay? Because we don't want to make our life difficult. Use the simplest equation. You're welcome to use the quadratic function, but the maths becomes difficult. So let's avoid it. Next question. The velocity of a truck moving along a straight road decreased uniformly, which means we have a negative acceleration from 20, so that's my initial velocity, to 12, so that's my final, covers a distance of 64. If it hang on. If it continues to slow down at this rate, how much further will it drive before it comes to rest? So my final velocity is 0. So let's see. This is the situation. They're telling me that it's going at 20 meters per second, ends up at 12, and that takes 64 meters. Then it goes for another distance and ends up stopping. Okay? What you need to recognize here is that the acceleration from 20 to 12 is the same acceleration from 12 to 0. I need to know that value in order to work out that delta x. So we're going to separate this into two sections. Part 1 is the 64 meters. I'm going to work out the acceleration using vf squared equals vi squared plus 2a delta x. Okay, I know vf, I know vi, I know delta x. I get minus 2 meters per second squared. I can leave it as minus 2. It's not my final answer. Okay? So I don't need to put it as in direction and words. But I do need to recognize that it's minus 2. So this is also minus 2. Now, we can go for the second part. My final velocity is now 0. My initial velocity is 12. Remember, I'm looking at this second part. I don't need to consider this 20 anymore. I just want delta x for the last part. So now I get 36. If I get a negative answer here, then I know I've made a mistake, because then somehow it's managed to go backwards, which it should never have been able to do because it was going forward the whole time. That tells me that the track moves a further 36 meters forward. In other words, it travels a total distance of 100. Alright, you now need to work on some examples, and hopefully that makes sense to you.